Voyager 1 detected something impossible at the edge of our solar system. A wall of superheated plasma reaching temperatures of 90,000 degrees Fahrenheit. Hot enough to vaporize any known material instantly. Yet the spacecraft sailed right through it, instruments still functioning, still transmitting data back across billions of miles of empty space. What scientists found at that boundary changed everything we thought we knew about where our solar system ends and true interstellar space begins. On August 25th, 2012, at precisely 121 astronomical units from the Sun, Voyager 1's instruments recorded something extraordinary. The steady stream of particles from our Sun, particles that had surrounded the spacecraft for its entire 35-year journey, suddenly dropped. Not gradually, not over weeks or months. Within hours, solar particles decreased by a factor of 1,000. At the exact same moment, cosmic rays from distant supernova explosions increased by 9%. The spacecraft had crossed a threshold that no human-made object had ever reached before. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. But here's what makes this discovery truly unsettling. Scientists didn't immediately realize what had happened. The data was confusing, contradictory even. Some instruments suggested Voyager had entered interstellar space. Others indicated it was still within the Sun's domain. It took nearly a year of analysis, debate, and additional measurements before NASA finally announced that yes, Voyager 1 had left the solar system. Not because the evidence was unclear, but because what the spacecraft found at that boundary defied every prediction scientists had made. Think about what this means for a moment. We've been studying the Sun for centuries. We've sent dozens of spacecraft throughout the solar system. We've mapped planetary orbits with extraordinary precision, predicted eclipses thousands of years in advance, and calculated the gravitational influence of objects billions of miles away. Yet when we finally reached the edge, when we sent our most sophisticated instruments to measure the boundary itself, we discovered we'd gotten it fundamentally wrong. The region Voyager encountered isn't smooth or gradual. It's turbulent, violent, and far more complex than anyone imagined. The temperature readings alone should have been impossible. Inside our solar system, temperatures decrease as you move away from the Sun. Basic physics. Yet at the heliopause, the actual boundary between solar and interstellar space, temperatures spike to tens of thousands of degrees. Not everywhere, mind you. The heat comes in patches, creating a chaotic mosaic of superheated plasma next to regions that are relatively cool. Scientists started calling it the Wall of Fire, though that name barely captures the strangeness of what's actually happening there. Now, you might wonder how a spacecraft survives temperatures that would instantly vaporize steel. The answer reveals something fundamental about the nature of space itself. Temperature measures the average kinetic energy of particles, how fast they're moving, how violently they're vibrating. But in the near-perfect vacuum at the edge of the solar system, there are so few particles that even though each individual particle carries enormous energy, they're so spread out they can't transfer that heat effectively. Voyager passes through this inferno like a ghost through walls, barely touched by the extreme conditions surrounding it. But the temperature anomaly was just the beginning of the surprises. The spacecraft's magnetometer detected something equally baffling. Based on decades of theoretical work, scientists predicted that the magnetic field beyond the heliopause would point in a significantly different direction than the magnetic field inside our solar system. Every model, every simulation, every calculation suggested this should be true. When Voyager 1 crossed the boundary, the magnetic field remained parallel to the solar magnetic field, exactly parallel, as if the boundary didn't exist at all, at least not magnetically. Voyager 2 confirmed this 6 years later when it made its own crossing at 119 astronomical units. Same result, same inexplicable alignment. Scientists are still struggling to understand why. The magnetic field is supposed to change direction at this boundary. That's what the physics predicts. That's what should happen. But it doesn't. And nobody can explain why the magnetic fields on both sides of this cosmic border behave as if they're connected, aligned, following rules we haven't discovered yet. Let me take you back to how we even knew where to look for this boundary. The story starts in 2004, 8 years before Voyager 1's historic crossing. The spacecraft had been traveling outward for 27 years at that point, moving through a region scientists thought was relatively well understood. Then, on December 16th, Voyager 1's instruments detected an abrupt change. The solar wind, that constant stream of charged particles flowing outward from the sun at roughly 1 million miles per hour, suddenly slowed down. Not gradually, abruptly. Within a matter of days, the solar wind went from supersonic to subsonic. This region became known as the termination shock, and it was the first major surprise. Scientists expected the solar wind to slow down, sure, but they expected it to slow to maybe a few 100,000 miles per hour. Instead, Voyager measured speeds that were drastically lower. In some cases, the wind seemed to be flowing backward toward the sun. That shouldn't happen. The sun's radiation pressure pushes everything outward, always. Yet here was direct evidence of solar wind moving in the wrong direction. 3 years later, Voyager 2 hit its own termination shock at 83.7 astronomical units. Different location, different distance from the sun. This told scientists something crucial. The solar system isn't a perfect sphere. It's lopsided, compressed on one side, elongated on the other. The sun is moving through interstellar space at about 26 kilometers per second, and that motion creates a shape more like a comet than a bubble. The leading edge, where we're pushing through the interstellar medium, is compressed and closer to the sun. The trailing edge stretches out behind us for potentially thousands of astronomical units. But the termination shock revealed other mysteries too. The magnetic field behavior was bizarre. Inside the solar system, as the sun rotates every 26 days, the direction of the interplanetary magnetic field alternates every 13 days. This creates a pattern scientists describe as zebra stripes. Alternating bands of magnetic polarity moving outward with the solar wind. Before the termination shock, these stripes passed Voyager quickly. After crossing the shock, the pattern slowed down dramatically. It took more than 100 days for a single stripe to pass the spacecraft. The solar wind had slowed down that much, and then there was the cosmic ray mystery. Scientists predicted that cosmic rays, high-energy particles from distant supernova explosions, would reach their maximum intensity at the termination shock. These particles are constantly trying to penetrate into our solar system, but the solar wind pushes back against them. At the shock, where the solar wind slows down dramatically, scientists expected cosmic rays would pile up, creating an intense radiation zone. That's not what Voyager found. The intensity of cosmic rays at the shock was lower than expected, and as Voyager moved beyond the shock, deeper into the region between the shock and the heliopause, the cosmic ray intensity kept increasing. It's still increasing today, even though Voyager is now well into interstellar space. This suggests something profoundly strange. There's a source of cosmic rays somewhere in the outer solar system that we haven't identified yet. Maybe it's at the heliopause itself. Maybe it's in the region beyond. But these particles are being generated or accelerated by some process we don't understand, in a location we can't precisely pinpoint. Between 2004 and 2012, Voyager 1 traveled through what scientists call the Helios Heath, the region between the termination shock and the heliopause. This is where things got really weird. In 2011, the spacecraft entered what researchers later termed the stagnation region. Solar wind speeds dropped to nearly zero. Particles that should have been streaming outward from the sun were instead moving inward. The magnetic field strength doubled. It was as if interstellar space was pushing back against our solar system, creating a zone of compression and confusion where the rules stopped making sense. Scientists hadn't predicted this region. It didn't appear in any of the models. Yet there it was, a vast zone spanning multiple astronomical units where the solar wind essentially stalled out, trapped between the outward pressure from the sun and the inward pressure from interstellar space. Some researchers started calling it cosmic purgatory, a fitting name for a region that seemed to belong neither to our solar system nor to the space beyond it. And throughout this entire journey, Voyager was measuring something else that would prove crucial for determining when it actually crossed into interstellar space. The spacecraft carries an instrument called the Plasma Wave Subsystem, essentially two 30-foot antennas sticking out behind it like bunny ears. This instrument can detect oscillations in the plasma surrounding the spacecraft. When solar eruptions send shockwaves through space, the plasma rings like a bell, vibrating at a frequency that depends on how dense it is. The denser the plasma, the higher the frequency. For years, this instrument detected only sporadic bursts, brief moments when solar storms sent ripples through the Helios sheath. But on April 9th, 2013, 8 months after Voyager had supposedly crossed the heliopause, the instrument began detecting continuous oscillations at 2.6 kilohertz. This frequency corresponded to a plasma density about 80 times higher than what Voyager had measured in the Helios sheath. That's exactly the density jump you'd expect. when crossing from the solar-dominated heliosphere into the interstellar-dominated medium beyond. This measurement became the smoking gun. The particle data suggested Voyager had crossed the boundary. The magnetic field data created confusion, but the plasma density measurement provided the confirmation scientists needed. Voyager 1 had indeed entered interstellar space on August 25th, 2012. It just took us 8 months to figure it out because we had to wait for a solar storm strong enough to make the interstellar plasma ring clearly enough for our instruments to detect. 6 months after that first detection, the plasma rang again, louder this time, and at an even higher frequency. The density was increasing. Voyager was moving deeper into interstellar space, and the space itself was getting thicker, more substantial, more resistant. This wasn't supposed to happen either. Most models predicted relatively uniform conditions in the local interstellar medium. Instead, Voyager found that the density continues to climb the farther it travels from the heliopause. By October 2020, both Voyagers were reporting significant and unexpected density increases. The measurements implied that this wasn't just a local phenomenon around the heliopause. The entire region of space in front of our solar system, in the direction we're moving through the galaxy, appears to be denser than the regions to the sides or behind us. Scientists call this the Very Local Interstellar Medium, or VLISM, and we're discovering that it has large-scale structures we never suspected existed. What makes all of this particularly fascinating is that we're not just learning about the edge of our solar system. We're learning about the nature of the space between stars throughout the entire galaxy. Every star creates its own heliosphere. Every stellar wind pushes against the interstellar medium in exactly this way. By studying our local boundary in such detail, we're developing models that apply to stellar systems across the cosmos. And the discoveries keep coming. In 2020, Voyager 1's magnetometer registered an abrupt jump in magnetic field intensity. At the same time, plasma density measurements spiked upward. Scientists initially thought these were caused by shockwaves from solar eruptions propagating through interstellar space. But the anomalies didn't stop. They continued for months, then years. Some mission scientists now suspect these persistent changes might not be coming from the sun at all. They might represent some new type of interstellar structure that Voyager is encountering as it travels deeper into the space between stars. We're now at a remarkable point in the mission. Voyager 1 is currently 172 astronomical units from Earth, the most distant human-made object in existence. Voyager 2 trails behind at 143 astronomical units. Both spacecraft are still operational, still transmitting data, still making discoveries about a realm that no instruments had ever directly sampled before. The signals from Voyager 1 take over 23 hours to reach Earth, traveling at the speed of light. Commands sent from Earth take another 23 hours to reach the spacecraft. We're having a conversation with our most distant ambassador at a pace of nearly 2 days per exchange, but we're running out of time. The plutonium that powers both spacecraft is steadily decaying. Engineers estimate that by the mid-2030s, there won't be enough power left to run even a single scientific instrument. The Voyagers will continue their journey into the galaxy, silent and dark, carrying their golden records, humanity's message to any intelligence that might one day find them. But before that happens, before we lose contact with these extraordinary machines forever, they have more to tell us about the boundary they crossed and the strange new realm they're exploring. What they found at that wall of fire is forcing scientists to completely rethink how our solar system interacts with the galaxy at large. The source of those cosmic rays wasn't where anyone predicted it would be. Think about what Voyager scientists expected to find. The termination shock, that first major boundary where the solar wind slams into the interstellar medium, should have been the cosmic ray factory, particles bouncing back and forth across that turbulent interface, gaining energy with each pass like a cosmic pinball machine. By the time Voyager 1 reached it in December 2004, models confidently predicted the cosmic ray intensity would peak right there at 94 astronomical units from the Sun. Instead, the intensity kept climbing, past the shock, through the heliosheath, all the way to the heliopause and beyond. The cosmic rays are still intensifying today, nearly 2 decades after Voyager 1 crossed that first boundary. Something out there in the unexplored regions of the outer solar system, or perhaps in interstellar space itself, is accelerating particles to extraordinary energies in ways we don't understand. But the cosmic ray mystery was just one of 3 fundamental surprises waiting at the termination shock. The second involved the solar wind itself. Picture a stream of charged particles racing away from the Sun at over 1 million miles per hour. That's the solar wind in the inner heliosphere, a supersonic gale of plasma that shapes magnetic fields and buffets everything in its path. When this wind hits the termination shock, it should decelerate to subsonic speeds. Models predicted it would slow to a few 100,000 miles per hour. What did Voyager measure? Speeds far lower than that. At times, the solar wind appeared to nearly stop. Even stranger, it sometimes seemed to flow backward toward the Sun. The wind that had blown outward for 94 astronomical units was suddenly hesitating, stuttering, even reversing direction. Scientists found themselves looking at data that shouldn't exist. The solar wind was behaving like a river that suddenly forgot which way it was supposed to flow. The magnetic field added its own layer of strangeness. As the Sun rotates every 26 days, the interplanetary magnetic field alternates direction every 13 days. This creates a pattern. Scientists call it the zebra stripe pattern, moving outward with the solar wind. Inside the termination shock, these stripes pass Voyager relatively quickly as the spacecraft moves through them. Beyond the shock, the zebra moved at nearly the same speed as Voyager itself. It took over 100 days for a single stripe to pass the spacecraft. The magnetic field was switching directions in slow motion, as if time itself had thickened in that region. None of this matched the models. Scientists had built sophisticated computer simulations of the heliosphere's outer reaches. They'd incorporated decades of solar wind observations, magnetic field measurements, and plasma physics theory. The models were elegant, mathematically rigorous, and apparently wrong about some fundamental aspects of how this boundary region actually behaves. By late 2011, Voyager 1 had traveled another 19 astronomical units beyond the termination shock. That's when it discovered something nobody had predicted at all. A region scientists would later call cosmic purgatory. The formal name is the stagnation region. But that clinical term doesn't capture the strangeness of what Voyager found. This was a zone where the rules seemed to shift, where the solar system's influence and interstellar space's presence created something entirely unexpected. Charged particles streaming from the sun were slowing down and turning inward. The solar system's magnetic field doubled in strength, as if interstellar space itself was pressing inward, compressing everything. Energetic particles that originated in the solar system declined by nearly half. Meanwhile, high-energy electrons from outside increased 100-fold. Voyager had entered a boundary layer 8 astronomical units thick, a transitional zone that wasn't quite solar and wasn't quite interstellar. It was both and neither, a hybrid region where 2 domains met and mixed in ways the models had never anticipated. The stagnation region's inner edge sits approximately 113 astronomical units from the Sun. 8 astronomical units might not sound like much. It's roughly the distance from the Sun to Saturn. But at this scale, that's a massive zone of space exhibiting behavior that challenged fundamental assumptions about how heliospheres work. What happens when you need to confirm you've entered interstellar space, but the instrument designed to measure plasma died 30 years ago? Voyager 1's plasma science instrument failed back in 1980, long before the spacecraft reached the outer solar system. This instrument was supposed to directly measure the properties of charged particles, their density, temperature, and velocity. Without it, scientists had no straightforward way to detect the dramatic density increase that defines the heliopause. They needed another method, something indirect, clever. The answer came from those bunny ear antennas, 2 10-meter probes extending behind the spacecraft as part of the plasma wave subsystem. This instrument wasn't designed to measure plasma density directly. It was built to detect waves and oscillations in the plasma around the spacecraft. But in April 2013, nearly 8 months after Voyager's instruments suggested it had crossed the heliopause, those antennas picked up something remarkable. A tone, a pure frequency at about 2.6 kilohertz. Scientists recognized what they were hearing. When plasma is disturbed by a solar eruption sending shock waves through space, for example, it rings like a bell at its natural frequency. The electrons oscillate back and forth along magnetic field lines, and that oscillation frequency depends directly on how tightly packed those electrons are. The frequency Voyager detected corresponded to an electron density of 0.08 particles per cubic centimeter. That might sound sparse, and it is, but it's 80 times denser than the solar system's normal heliosphere. The definition of the heliopause is based precisely on this kind of density jump. Voyager was hearing interstellar space ring. 6 months later, another whistle appeared. This one was louder and higher pitched. The density had increased further. The interstellar medium was getting thicker as Voyager traveled deeper into it. These plasma waves provided scientists with a continuous measure of density changes in interstellar space. As Voyager pushed farther from the heliopause, the waves kept coming, sometimes triggered by solar storms, whose shockwaves followed the spacecraft into interstellar space. Sometimes, from sources scientists are still trying to identify. Each detection refined understanding of the boundary Voyager had crossed. Each measurement revealed more about the structure of the space beyond. But perhaps the most unsettling discovery came from comparing the two crossings, Voyager 1 in 2012 and Voyager 2 in 2018. They should have been similar. Both spacecraft were built identically. Both carried the same instruments. Both crossed at nearly the same distance from the Sun, 121.6 astronomical units for Voyager 1, 119 astronomical units for Voyager 2. That consistency seemed to suggest the heliopause maintained a relatively stable position, except the crossings happened under completely different solar conditions. Voyager 1 crossed during solar maximum, when the Sun's activity peaks. Voyager 2 crossed during solar minimum, when the Sun is at its quietest. Scientists expected these different solar conditions to produce measurably different boundary characteristics, and they did, just not in ways anyone anticipated. Voyager 1 observed the solar wind dropping to nearly zero as it approached the heliopause. The wind essentially died before the crossing. But Voyager 2 measured relatively high solar wind speeds almost all the way through until the moment it crossed the boundary. Voyager 2's data suggested a thinner, smoother heliopause than what Voyager 1 encountered. Both spacecraft apparently traversed the boundary in less than a day, but the character of that crossing differed significantly. The magnetic field alignment provided yet another puzzle. Scientists expected the interstellar magnetic field to be oriented differently from the solar magnetic field. These are two independent magnetic structures meeting at a boundary. There's no reason they should align. Voyager 1 found them largely parallel. When Voyager 2 crossed 6 years later, it confirmed the same surprising result. The magnetic fields on both sides of the heliopause were aligned in the same direction. This is one of those findings that sounds technical but carries profound implications. The mechanism that could produce this alignment isn't understood. The physics that would allow two independent magnetic fields to coordinate across a boundary without any obvious coupling mechanism remains mysterious. Scientists must come to some understanding of why this happens. The current models don't explain it. The observations from other missions don't predict it. It's a fundamental feature of the heliosphere's boundary that the theories got wrong. Then there's the particle leakage. The heliopause isn't supposed to be permeable. It's the boundary where the solar wind's pressure balances the interstellar medium's pressure. That definition suggests a clear demarcation. Solar particles on one side, interstellar particles on the other. Reality is messier. Voyager detected interstellar particles inside the heliosphere on 2 separate occasions before crossing the boundary. The mission team attributed these detections to interstellar flux tubes, structures where the magnetic field allows particles to penetrate deeper than they should. If the heliosphere is like a ship sailing through interstellar space, the hull appears somewhat leaky. Voyager's instruments showed particles from inside the heliosphere slipping through the boundary into interstellar space. The leakage isn't uniform. Voyager 1 exited near the heliosphere's front where the boundary seems more robust. Voyager 2 crossed closer to the flank, where the region appears more porous. This asymmetry matters. It reveals that the heliopause isn't a simple spherical boundary. It has structure, variation, regions of different permeability. The heliosphere itself has a shape more complex than early models suggested. Both spacecraft also recorded increased plasma density before and after crossing the boundary. The density increase on the solar side suggests compression. The solar wind piling up against the barrier. The density increase on the interstellar side suggests the same thing in reverse. The interstellar medium compressing against the heliosphere's outer surface. This double compression creates a boundary layer where both domains press against each other with measurable force. The higher than expected density on the interstellar side indicates that interstellar pressure may be shaping the heliosphere more actively than models predicted. The temperature dynamics at this boundary exceed anything scientists expected. Near the heliopause, charged particles become trapped and compressed. This compression generates heat, extraordinary heat. Temperatures reach 30,000 to 50,000 Kelvin in some regions. That's 54,000 to 90,000 degrees Fahrenheit. Hot enough to ionize nearly anything. Hot enough to create what some researchers have called the wall of fire. But here's the remarkable part. The particle density is so low that this heat doesn't transfer to spacecraft. Voyager passed through these super hot regions without any thermal damage. The heat exists, but it exists in such a sparse medium that it can't effectively conduct to solid objects. The temperature isn't uniform either. Nearby regions remain relatively cooler. The boundary creates a patchwork of hot and cold plasma, unlike anything observed inside the heliosphere. The temperature variations are extreme and patchy, far more chaotic than models predicted. As Voyager approached the heliopause, its instruments recorded sudden changes in particle density and magnetic fields. These weren't the smooth, gradual transitions scientists expected. They were abrupt shifts, almost like stepping across a threshold. The boundary between solar and interstellar space turned out to be sharp in some ways, fuzzy in others, and structured in ways nobody had fully anticipated. Now, both Voyagers continue deeper into interstellar space, and the discoveries keep coming. The density continues to rise. The magnetic field measurements keep revealing unexpected patterns. The persistent anomalies that began in 2020 still haven't been fully explained. Scientists are piecing together what these measurements mean for our understanding of how stars interact with the galaxy at large. The instruments paint a picture of interstellar space that nobody anticipated. Voyager's plasma wave instrument, those two bunny ear antennas extending 30 feet behind the spacecraft, started picking up something strange in April 2013. A tone, a persistent hum. The electrons in the interstellar plasma were ringing like a struck bell, vibrating at 2.6 kilohertz. This frequency revealed something critical about the density of the space Voyager had entered. The pitch of the ringing directly correlates to how tightly packed the electrons are. Higher frequency means higher density. Inside the heliosphere, the density measured about 0.001 electrons per cubic centimeter. Sparse, empty, The plasma wave instrument rarely detected anything worth noting, just occasional bursts when solar eruptions sent shock waves rippling outward. Beyond the heliopause, that 2.6 kHz tone indicated a density of 0.08 electrons per cubic centimeter, 80 times denser than the heliosphere's interior. This density jump wasn't just confirmation of the crossing. It fundamentally defined what the heliopause is. The boundary exists precisely where this density transition occurs. The sharp increase in particle concentration creates the physical barrier between solar and interstellar domains. 6 months later, the tone changed again, louder, higher pitched. The interstellar medium was getting thicker, fast. Before Voyager, scientists had only theoretical models to predict interstellar density. Now they had measurements, real data from beyond the edge. The measurements revealed something unexpected. Density wasn't constant. It varied. The plasma wave instrument detected continuous emissions, where it previously only caught sporadic bursts. These persistent waves provided an ongoing measure of local conditions as Voyager traveled deeper into interstellar territory. The discovery raised immediate questions. Why was density increasing so rapidly? What structures existed in the very local interstellar medium that could create these variations? By October 2020, both Voyagers were reporting significant density increases. The measurements implied something profound about the regions surrounding our solar system. The density gradient wasn't just local noise. It appeared to be a large-scale feature of the very local interstellar medium, particularly in the direction of the heliospheric nose, the leading edge of our solar system's motion through the galaxy. Think about what this means. Our solar system isn't traveling through uniform space. We're moving through a structured medium with varying density, pressure, and composition. The local interstellar cloud through which we're currently passing has internal architecture, regions of compression, zones of rarefaction, gradients that shift over distances measured in astronomical units. The cosmic rays tell another story entirely. For 6 years before crossing the heliopause, Voyager 1 measured a steady rise in high-energy particle collisions, cosmic rays with energies above 70 million electron volts. These particles originated far beyond our solar system, accelerated by supernova explosions and other violent galactic events. Then came late August 2012. The cosmic ray intensity spiked sharply. Simultaneously, low-energy particles from the Sun dropped by a factor of 1,000. August 25th, 2012. The day everything changed. Voyager 1 recorded a 1,000-fold decrease in charged solar particles. At the same moment, galactic cosmic ray intensity increased by 9%. The shift was dramatic, unmistakable. Solar particles streamed away into interstellar space. Galactic particles flooded in from beyond. This particle swap provided some of the clearest evidence that Voyager 1 had crossed into a fundamentally different environment. The heliosphere had been filtering these cosmic rays, blocking more than 70% of the galactic radiation that would otherwise reach Earth's orbit. Voyager 2's crossing revealed additional complexity. Just beyond the heliopause, it discovered a boundary layer where low-energy particles still streamed outward along magnetic field lines. Cosmic ray intensities in this layer reached only 90% of levels measured farther out. A transition zone, not a clean break. The heliopause isn't a wall. It's a gradient with structure, a region where solar and interstellar influences blend and compete before one domain finally dominates. The cosmic ray measurements also exposed something unexpected about their origins. Scientists had predicted that interstellar ions would bounce back and forth across the termination shock, slowly gaining energy with each bounce until they became high-speed cosmic rays. The intensity of these accelerated particles should have peaked at the shock itself. It didn't. Cosmic ray intensity failed to reach maximum at the termination shock. Instead, it kept increasing as Voyager traveled farther beyond the shock. The measurements suggested the source of these particles lay in a region of the outer solar system yet to be discovered. Somewhere between the termination shock and the heliopause, or perhaps beyond, cosmic rays were being accelerated by mechanisms scientists didn't fully understand. The magnetic field behavior proved equally puzzling. Both Voyagers carried magnetometers designed to measure field strength and direction. Scientists expected dramatic changes when the spacecraft crossed into interstellar space. The interstellar magnetic field should differ significantly from the heliospheric field in both magnitude and orientation. Voyager 1 crossed in 2012. Its magnetometer showed the interstellar field aligned largely parallel to the heliospheric field. Strange, but perhaps explicable as a local anomaly or measurement artifact. Voyager 2 crossed in 2018 at a different location during different solar conditions. Its magnetometer confirmed the same result. The interstellar field remained parallel to the heliospheric field. This alignment contradicted predictions based on observations from other missions and theoretical models. The magnetic field should have rotated, twisted, or at least changed direction as the spacecraft transitioned between domains. The fact that it didn't indicate something fundamental about the interaction between solar and interstellar magnetic fields that current physics doesn't explain. Scientists must come to some understanding of why the magnetic field doesn't change. That process remains simply not understood. The parallel alignment suggests the two fields are somehow coupled or influenced by structures operating on scales larger than the heliosphere itself. Perhaps the local interstellar cloud's magnetic field naturally aligns with our Sun's field due to their mutual motion through the galaxy. Perhaps magnetic reconnection events at the heliopause create channels that enforce alignment. Perhaps the physics of magnetic field interactions at this boundary differs from anything we've modeled. Nobody knows yet. The magnetic field measurements revealed another peculiarity near the termination shock. The Sun rotates every 26 days, which causes the interplanetary magnetic field to alternate direction every 13 days. This alternating pattern creates a structure like zebra stripes moving outward with the solar wind. Before reaching the termination shock, these stripes moved past Voyager at predictable intervals. After crossing the shock, the pattern changed dramatically. The stripes started moving at nearly the same speed as Voyager itself, stretched and distorted by the shock's effects. It took more than 100 days for a single stripe to pass the spacecraft and for the magnetic field to switch directions. The stretching indicated the termination shock wasn't just slowing the solar wind, it was fundamentally altering how the sun's magnetic field propagated through space. Then came 2020. Voyager 1's magnetometer registered an abrupt jump in the intensity of magnetic fields embedded in the interstellar plasma. Simultaneously, the plasma detector measured a rise in plasma density. The jumps appeared transient at first, temporary fluctuations that would fade. They didn't fade. The anomalies persisted through 2020, 2021, and beyond. Researchers initially attributed the changes to surges of solar plasma smashing against the heliosphere's boundary, creating swells that reverberated through interstellar space. Solar activity can compress interstellar plasmas and intensify their magnetic fields even at distances of 120 astronomical units. But the anomalies didn't abate. The magnetic field intensity remained elevated. The plasma density stayed high. Some mission scientists began questioning whether these effects originated with the Sun at all. Perhaps Voyager had entered a new type of interstellar structure. Perhaps the very local interstellar medium contained regions of enhanced density and magnetic field strength that weren't connected to solar activity. The mystery remains unresolved. Voyager continues transmitting data, and that data continues revealing patterns nobody anticipated. The spacecraft are exploring genuinely unknown territory, encountering phenomena that challenge existing models of how interstellar space operates. The heliosphere itself responds to the 11-year solar activity cycle. The heliopause isn't static. It breathes like a lung, expanding and contracting as solar output varies. During solar maximum, when the sun's activity peaks, the solar wind blows harder and pushes the heliopause farther out. During solar minimum, when the sun quiets, the boundary contracts inward. This dynamic behavior means future spacecraft crossing the heliopause might encounter it at different distances depending on when they arrive. The boundary isn't a fixed landmark in space. It's a moving target, responsive to both solar cycles and variations in the interstellar medium pressing against it from the outside. Voyager 1 crossed during solar maximum at 121.6 astronomical units. Voyager 2 crossed during solar minimum at 119 astronomical units. The distances were nearly identical despite vastly different solar conditions. This consistency struck scientists as very strange. It suggested the heliopause's position might be more strongly influenced by interstellar pressure than by solar wind strength. The two crossings also revealed differences in the boundary's character. Voyager 1 observed solar wind speeds dropping nearly to zero, close to the heliopause. Voyager 2 measured relatively high solar wind speeds almost all the way through until crossing. Voyager 2's data suggested a smoother, thinner heliopause than Voyager 1 encountered. Both spacecraft apparently traversed the boundary in less than a day. Crossing didn't take weeks or months. It happened fast, reinforcing the idea that the heliopause is sharp rather than gradual, at least on scales relevant to spacecraft motion. The differences between the two crossings illuminate how location and timing affect what spacecraft observe. The heliosphere isn't symmetric. Its shape gets compressed and distorted by the interstellar medium's pressure and magnetic fields. Voyager 1 exited near the nose. the front of the heliosphere relative to our motion through the galaxy. Voyager 2 exited closer to the flank. These different exit points sampled different regions of the boundary, revealing variations in thickness, permeability, particle flow, and magnetic field behavior. The heliosphere has texture, structure, regions where the boundary behaves differently depending on local conditions. The plasma environments on either side of the heliopause differ fundamentally. Inside, the plasma is hot and sparse, heated by the sun and blown outward at high speed. Outside, the plasma is cold and dense, part of the ancient interstellar cloud through which our solar system happens to be traveling. Hot but sparse versus cold but dense. The difference defines the boundary. The temperature contrast creates the zones of extraordinary heat near the heliopause, where particles become trapped and compressed. The density contrast creates the sharp transition that Voyager's instruments detected. The magnetic field differences, or lack thereof, create the ongoing mystery that scientists are still working to explain. Understanding these plasma properties matters beyond just characterizing our local cosmic neighborhood. Every star in the galaxy creates its own heliosphere, a bubble carved out of the interstellar medium by stellar wind. Studying how our sun's bubble interacts with surrounding space provides insights into stellar physics throughout the universe. The measurements Voyager continues sending back help scientists model not just our heliosphere, but heliospheres around other stars. They reveal universal principles about how stellar winds interact with interstellar matter, how magnetic fields behave at boundaries, how cosmic rays propagate through different environments. And Voyager keeps going. Both spacecraft continue deeper into interstellar space at roughly 3 astronomical units per year. Voyager 1 now travels at 172 astronomical units from Earth, the most distant human-made object in existence. Voyager 2 follows at 143 astronomical units. The spacecraft will eventually run out of power. The plutonium that fuels their radioisotope thermoelectric generators decays steadily, producing less electricity each year. Mission controllers have been shutting down non-essential systems to conserve power. The heaters keeping instruments warm get turned off. Redundant systems get disabled. By the mid-2000s, both Voyagers will likely go silent. Their transmitters will fail. Their instruments will freeze. They'll become inert artifacts drifting through the galaxy, carrying golden records intended for civilizations that might find them millions of years from now. But for now, they're still active, still transmitting, still revealing what exists beyond the edge of everything humans had previously explored. The data coming back from interstellar space revealed something nobody anticipated. In 2020, Voyager 1's magnetometer registered an abrupt jump in magnetic field intensity. The plasma detector simultaneously measured rising plasma density. Researchers initially assumed these spikes came from solar eruptions, plasma surges from the sun, smashing against the heliosphere's boundary, creating reverberations that compressed interstellar plasma and intensified magnetic fields. Temporary disturbances that would fade, but the anomalies didn't stop. They continued. Month after month, the measurements showed persistent changes that didn't match patterns from solar activity. Scientists started questioning whether these signals originated with the Sun at all. Maybe Voyager was detecting something else entirely, a structure in interstellar space itself, some feature of the local interstellar medium that previous models hadn't predicted. The very local interstellar medium, abbreviated VLISM, turned out to be more complex than expected. Before crossing the heliopause, scientists imagined interstellar space as relatively uniform, empty, quiet, a void between stars where plasma drifted slowly and magnetic fields barely fluctuated. Voyager's instruments painted a different picture. The VLISM has texture, structure, variations in density that change over surprisingly short distances. The plasma isn't uniformly distributed, but forms gradients, regions where particles concentrate more densely than surrounding areas. In October 2020, astronomers reported significant unexpected increases in density detected by both Voyagers. The measurements implied that the density gradient is a large-scale feature of the VLISM in the general direction of the heliospheric nose, the front of the heliosphere, relative to our motion through the galaxy. As Voyager continues outward, it's traveling through a region where the local interstellar medium is being compressed or is naturally denser than previously expected. This has implications for understanding the structure of the local interstellar cloud through which our solar system happens to be moving. Our solar system isn't stationary. It moves through the galaxy at roughly 26 kilometers per second relative to nearby stars. That motion carries us through different regions of interstellar space, clouds of gas and dust with varying properties. Currently, we're passing through what's called the local interstellar cloud, sometimes referred to as the local fluff. It's a region of slightly higher density than average interstellar space, with temperatures around 6,000 Kelvin and particle densities of about 0.3 atoms per cubic centimeter. That's still incredibly empty by Earth standards, a better vacuum than anything achievable in laboratories. But it's denser than the average between-star environment. The local interstellar cloud itself sits inside a larger structure called the local bubble, a region hundreds of light years across where ancient supernova explosions swept away most of the gas, leaving a cavity of extremely low-density space. Our solar system is near one edge of this bubble, moving through one of the denser clouds within it. Voyager's measurements help map these structures, revealing details about the interstellar environment that surrounds our cosmic neighborhood. One of the most surprising findings from the VLISM involves plasma waves. Voyager 1's plasma wave instrument, those two bunny ear antennas extending 10 meters behind the spacecraft, detected sporadic bursts of plasma oscillations for years, brief whistles when solar eruptions sent shock waves rippling through interstellar space, making the plasma ring like a struck bell. But in the sparse collection of atoms filling interstellar space, Voyager eventually started detecting something different, long-lasting series of waves where it previously only detected occasional bursts, continuous emissions that provided an ongoing measure of plasma density. These waves vibrate electrons back and forth along magnetic field lines. The electrons ring out at characteristic frequencies, depending on how closely packed they are. Higher pitch means higher density. 6 months after the first continuous detection, another whistle appeared, louder and even higher pitched. The interstellar medium appeared to be getting thicker, quickly. The discovery of these persistent plasma waves was unexpected. Scientists hadn't predicted continuous emissions. The finding provides valuable data about the structure and properties of the very local interstellar medium as Voyager travels through it. The plasma density Voyager measures in interstellar space is about 0.08 particles per cubic centimeter, roughly 80 times denser than the heliosphere's interior. That jump in density defines the heliopause. But the density isn't constant. It varies, sometimes gradually, sometimes abruptly. The variations suggest that interstellar space has a complex structure with regions of different particle concentration. Voyager is essentially taking a core sample through the VLISM, measuring properties along a single line as it moves outward. Each measurement reveals details about the environment at that specific location. Scientists can extrapolate from Voyager's trajectory to make educated guesses about surrounding regions, but there's no way to know for certain what exists a few astronomical units to the side of Voyager's path without sending another spacecraft. The VLISM remains mostly unmapped. 2 data points, Voyager 1 and Voyager 2, traveling through an ocean of space, sending back measurements from wherever they happen to be. It's like trying to understand Earth's entire ocean by taking samples from 2 ships sailing in roughly the same direction, separated by several hundred miles. Still, those 2 ships have revealed fundamental truths about the ocean they're crossing. The magnetic field measurements proved particularly illuminating. Both Voyagers confirmed a result that contradicted theoretical predictions. The magnetic field in the region just beyond the heliopause runs parallel to the magnetic field inside the heliosphere. Scientists expected significant differences in field direction. Models suggested the interstellar magnetic field should be oriented differently from the solar magnetic field, creating a rotation or twist at the boundary. Neither Voyager detected that rotation. The fields aligned. Scientists don't understand why. The process that produces this alignment remains unexplained. Magnetic fields in space form when charged particles move through plasma. The sun's rotation and the outward flow of solar wind create the heliosphere's magnetic field, which gets dragged along by the solar wind like a garden hose whipping around as water flows through it. The interstellar magnetic field comes from different sources: galactic rotation, ancient supernova remnants, the motion of gas clouds through the galaxy. These fields should be independent, unrelated, yet at the boundary, they somehow line up. The alignment suggests some physical mechanism at the heliopause causes the fields to couple or synchronize. Or maybe the interstellar magnetic field in this particular region of space happens to be oriented similarly to the heliospheric field by coincidence. Neither explanation is entirely satisfying. The mystery highlights how much remains unknown about magnetic field behavior in space plasmas. Laboratory experiments can't replicate the conditions at the heliopause. The enormous scales, the incredibly low densities, the weak magnetic fields. Computer simulations help but require assumptions about plasma physics that might not hold true in all environments. Voyager's measurements provide ground truth, real data from the actual boundary. And that data reveals gaps in our understanding. Cosmic rays present another puzzle. High-energy particles accelerated by supernova explosions and other violent galactic events. Before Voyager crossed the heliopause, scientists predicted cosmic ray intensity would reach maximum at the termination shock, the boundary where solar wind slows abruptly. Theoretical models suggested interstellar ions would bounce back and forth across the shock, gaining energy with each bounce until they became high-speed cosmic rays. The shock should be where cosmic rays concentrate most intensely. But Voyager 1 found the opposite. Cosmic ray intensity didn't peak at the shock. It kept increasing as Voyager moved farther beyond the shock. The intensity continued rising through the heliosheath and into interstellar space. This pattern suggests the source of cosmic rays lies in a region scientists hadn't predicted. Somewhere beyond the heliopause, in interstellar space itself, cosmic rays are being accelerated or concentrated. Maybe the heliopause acts as a kind of cosmic ray filter, allowing only the highest energy particles to pass inward, while reflecting lower energy ones back into interstellar space. Or maybe there's a region just beyond the heliopause where magnetic field interactions accelerate particles. The measurements from both Voyagers show cosmic ray intensity is about 90% of what's detected farther out when they're just beyond the boundary, then increases to full interstellar levels within a few astronomical units. A boundary layer exists where cosmic ray intensity transitions from heliospheric to fully interstellar values. Understanding cosmic ray behavior matters for more than academic curiosity. Cosmic rays pose radiation hazards to spacecraft and astronauts. They can damage electronics, degrade solar panels, and increase cancer risk for humans in space. Knowing how cosmic rays propagate through different environments helps mission planners design better shielding and assess radiation exposure for future deep space missions. Voyager's measurements revealed that the heliosphere shields Earth and other planets from more than 70% of galactic cosmic radiation. Without that protection, life on Earth would face significantly higher radiation levels. The heliosphere functions as a magnetic bubble that deflects or slows cosmic rays before they reach the inner solar system. Lower energy cosmic rays get deflected entirely. Higher energy ones penetrate but lose energy as they fight through the outward flowing solar wind and tangled magnetic fields. Only the most energetic cosmic rays make it all the way to Earth's orbit without significant energy loss. This filtering effect changes with solar activity. During solar maximum, when the Sun's magnetic field is strongest and most complex, cosmic ray intensity at Earth decreases. During solar minimum, more cosmic rays penetrate to the inner solar system. The 11-year solar cycle creates corresponding variations in cosmic ray exposure. Voyager's journey beyond the heliosphere also revealed details about the heliosphere's shape. Early models assumed a roughly spherical bubble. The termination shock and heliopause would form concentric shells around the Sun, symmetric in all directions. Voyager's measurements showed that assumption was wrong. The heliosphere is asymmetric, compressed, distorted by external pressure from the interstellar medium and by magnetic fields draped around it. The overall shape resembles a comet more than a sphere, roughly rounded on one side, with a long tail extending in the opposite direction. The tail, called the heliotail, stretches for thousands of astronomical units downstream from the Sun's motion through the galaxy. Solar wind that flows out the backside of the heliosphere gets swept into this tail, creating an elongated structure that trails behind like a cosmic contrail. The heliotail has never been directly observed. No spacecraft has traveled in that direction. But models based on Voyager's measurements and observations from the Interstellar Boundary Explorer satellite suggest it exists. Mapping its structure remains a goal for future missions. The heliosphere's asymmetry explains why Voyager 1 and Voyager 2 crossed the termination shock at different distances. 94 astronomical units for Voyager 1, 83.7 for Voyager 2. The boundary isn't spherical. It's closer to the Sun in some directions than others. The interstellar magnetic field tilts relative to the direction of the interstellar flow, creating pressure that pushes the southern hemisphere of the heliosphere inward. The termination shock forms an offset sphere, pushed back in the direction we're moving through the galaxy, closer in other directions, with the whole structure tilted and compressed. The heliosphere also breathes. Its size changes in response to solar activity. During solar maximum, increased solar wind pressure pushes the heliopause outward. During solar minimum, reduced pressure allows the heliopause to contract. The boundary moves in and out like a lung expanding and contracting with breath. This dynamic behavior means future spacecraft crossing the heliopause might encounter it at different distances depending on where the Sun is in its activity cycle. The heliopause isn't a fixed boundary, but a moving interface that responds to changing conditions on both sides. Voyager's measurements quantified how much the heliopause can move. The difference between solar maximum and minimum can shift the boundary by 10 to 20 astronomical units, billions of kilometers. That's significant. A spacecraft approaching the heliopause might find it farther away than expected if the Sun's activity has increased since mission planning began, or closer if activity has decreased. Understanding this variability helps scientists interpret measurements and predict where future spacecraft will encounter the boundary. And what about the bow shock? Early models predicted the Sun's motion through the interstellar medium would create a bow shock ahead of the heliosphere, similar to the shock wave that forms in front of a ship moving through water. The Interstellar Boundary Explorer satellite and Voyager data revealed something unexpected. There's no bow shock. The interstellar medium flows past the heliosphere without forming that predicted shock wave. This absence indicates the interstellar medium is moving subsonically relative to the Sun, slower than the speed of sound in that medium. Without supersonic relative motion, no bow shock forms. The missing bow shock changed scientific understanding of how the heliosphere interacts with its surroundings. Instead of a sharp shock wave, there's a gentler transition region, sometimes called the hydrogen wall, a region where neutral hydrogen from the interstellar medium piles up as it encounters the heliosphere's edge. Voyager spacecraft first detected this structure in 1992. New Horizons confirmed the detection in 2018. The hydrogen wall isn't as dramatic as a bow shock would be, but it represents an important boundary feature that affects how neutral atoms behave as they approach the heliosphere. Voyager continues revealing surprises about interstellar space. The spacecraft aren't done teaching us yet. The two Voyager spacecraft crossed the heliopause at nearly identical distances, 121 astronomical units for Voyager 1, 119 for Voyager 2. That similarity seems reasonable until you consider the timing. Voyager 1 crossed during solar maximum, when the Sun's activity peaks. Voyager 2 crossed during solar minimum, when activity drops to its lowest point. The heliopause should have been farther out during maximum, closer during minimum. But both spacecraft encountered it at essentially the same distance. Scientists call this consistency very strange. The crossings themselves differed in character. Voyager 1 measured solar wind speeds, dropping nearly to zero as it approached the boundary. The wind slowed, stalled, almost stopped. Then the spacecraft crossed over. Voyager 2 measured relatively high wind speeds almost until the moment of crossing. No gradual slowdown, no stalling zone, just steady flow, then transition. The boundary itself appeared smoother and thinner for Voyager 2. Voyager 1's crossing involved more turbulence, more back and forth fluctuations. Both spacecraft traversed the heliopause in less than a day, but the experience wasn't identical. Location matters. Voyager 1 exited near the front of the heliosphere, the direction the solar system moves through the galaxy. That's where the interstellar wind hits head-on. Voyager 2 crossed closer to the flank, off to the side. The heliopause behaves differently in different locations. It's not uniform, not consistent. The boundary's properties change depending on where you cross it, when you cross it, what the Sun's doing at that moment. Both spacecraft detected something unexpected at the heliopause: particle leakage. The boundary isn't sealed, it's porous. Particles from inside the heliosphere slip through into interstellar space. Particles from outside find their way in. Voyager 1 detected interstellar particles twice before crossing. Brief intrusions scientists attributed to interstellar flux tubes, channels or pathways allowing material to penetrate the boundary. The hull leaks, not catastrophically, but measurably. Voyager 2's location near the flank showed even more porosity. That region appears more permeable than where Voyager 1 crossed. The heliopause isn't a solid wall. It's more like a membrane, flexible, semi-permeable, with varying thickness and permeability, depending on location. Some regions seal tightly, others let particles drift across. This challenges the simple picture of a clean boundary separating two domains. The plasma environment on either side tells its own story. Inside the heliosphere, plasma is hot and sparse, heated by the sun, spread thin by the solar wind's expansion. Outside, in interstellar space, plasma is colder but denser. The temperature drops, the density rises. That density jump provided crucial evidence for Voyager's crossing. Voyager 1's plasma wave instrument detected electron plasma oscillations resonating at 2.6 kHz, a frequency corresponding to electron density, about 80 times higher than inside the heliosphere. That's the signature scientists needed. Proof of interstellar space. The measurement came with a twist. Voyager 1's direct plasma instrument failed in 1980. Decades before reaching the heliopause, engineers couldn't directly measure plasma properties. They needed indirect methods. The plasma wave instrument became the solution. When solar eruptions sent shockwaves through interstellar plasma, that plasma rang like a struck bell, vibrating at its natural frequency. The spacecraft listened to those vibrations. The frequency revealed the density. Problem solved through ingenuity. 6 months after the first detection, another whistle appeared, louder, higher pitched. The interstellar medium was getting thicker. Quickly, Voyager 1 discovered something else: continuous plasma wave emissions. Before crossing, the instrument detected only sporadic bursts. After crossing, it measured long-lasting waves reverberating through space. The electrons vibrated back and forth along magnetic field lines, creating oscillations that provided ongoing density measurements. Scientists could map variations in the local interstellar medium. As Voyager traveled through it, those variations matter. In October 2020, both Voyager spacecraft detected a significant, unexpected increase in density. The very local interstellar medium, the region immediately beyond the heliopause, showed a density gradient, a large-scale feature in the direction the heliosphere's nose points. The interstellar medium isn't uniform either. It has structure, regions of higher and lower density, variations that affect how the heliosphere interacts with its surroundings. The temperature dynamics at the boundary proved equally surprising. Scientists expected a smooth, gradual transition, cool solar wind meeting cool interstellar plasma. Instead, Voyager found extreme temperatures, 30,000 to 50,000 Kelvin in some regions. The boundary creates zones of extraordinary heat where charged particles become trapped and compressed. Other nearby regions stay relatively cooler. It's a patchwork. Hot and cold plasma mix together in patterns unlike anything inside the heliosphere. This earned the nickname Wall of Fire. Not because spacecraft burn up, the particle density is too low to transfer heat, but because of the temperature extremes. Researchers expected gradual fading between solar and interstellar environments. Voyager found abrupt shifts, almost like stepping over a threshold. One side, then the other. The transition isn't gentle. As spacecraft approached the boundary, instruments recorded sudden changes in particle density and magnetic fields, signatures of turbulence. The region is more chaotic than models predicted. The heliopause isn't a calm interface. It's dynamic, fluctuating, responding to pressure from both sides. And then there's the magnetic field mystery. Before Voyager 2 crossed, scientists expected significant differences between the heliospheric magnetic field and the interstellar field. Different directions, different orientations. That's what models predicted. That's what made sense based on observations from other missions. Voyager 1 found something different. The interstellar magnetic field aligned largely parallel to the heliospheric field. Same direction, similar orientation. That was unexpected, maybe an anomaly specific to where Voyager 1 crossed. Then Voyager 2 confirmed it. The same alignment, the same parallel orientation. Not an anomaly, a real feature. Scientists must understand why the magnetic field doesn't change direction at the heliopause. The process isn't understood. the physics remains unclear. Two independent measurements from two different locations at two different times show the same thing. The interstellar magnetic field and the heliospheric field align, somehow, for reasons still being investigated. This discovery contradicted predictions based on theoretical models and observations from missions like IBEX. It suggests the interaction between solar and interstellar magnetic fields is more complex than current understanding. The fields don't simply meet at the boundary and transition. They connect, they align, they interact in ways that preserve directional continuity across the heliopause. Understanding this matters beyond just satisfying curiosity. Magnetic fields govern how particles move, how energy transfers, how the heliosphere shields Earth from galactic cosmic rays. If the fields align unexpectedly, that changes how protection works. It changes predictions about space weather. It changes models of how stellar winds interact with interstellar environments, not just for our Sun, but for other stars throughout the galaxy. Voyager continues measuring magnetic field properties in interstellar space. The spacecraft traveled deeper into the very local interstellar medium, sending back data about field strength, direction, fluctuations. In 2020, Voyager 1's magnetometer registered abrupt jumps in field intensity. The plasma detector measured simultaneous rises in plasma density. These transient jumps appeared to originate from surges of solar plasma smashing against the heliosphere's boundary, creating swells that reverberate through interstellar space, compressing interstellar plasma, intensifying magnetic fields. But the anomalies didn't abate. They continued, persisted. Some mission scientists began questioning whether these changes originated with the Sun at all. Maybe they represent something else, a new type of interstellar structure, a region of naturally higher density or stronger fields. The mystery remains open. Voyager 1 discovered interstellar space is quiet. Magnetic fluctuation intensity is very small beyond the heliopause. Inside the heliosphere, the magnetic field constantly varies, responding to solar activity, solar wind turbulence, the rotating sun's changing output. Outside, fluctuations diminish. The field is more stable, more consistent. The interstellar environment doesn't experience the same constant stirring from stellar winds. That quietness contrasts with the boundary's violence. At the heliopause itself, conditions are turbulent, chaotic, extreme. But once you move away from that interface into true interstellar space, things calm. The environment stabilizes. It's not that interstellar space is empty or inactive. It has its own dynamics, its own variations, but it operates at a different rhythm than the heliosphere's constant solar-driven churn. The cosmic ray environment tells another story. Inside the heliosphere, low-energy particles dominate, mostly originating from the Sun. Galactic cosmic rays, high-energy particles accelerated by supernovae and other violent galactic events, are present but suppressed. The heliosphere blocks them, deflects them, reduces their intensity. At the heliopause, that changes dramatically. Voyager 1 recorded a 1,000-fold drop in solar particles simultaneous with a 9% increase in galactic cosmic rays. The shift happened over days. The solar particles disappeared. The cosmic rays surged. Voyager 1 discovered the heliosphere protects Earth and other planets from more than 70% of galactic radiation. Without that shield, surface conditions on Earth would be harsher. Life would face greater radiation exposure. Voyager 2 found a boundary layer just beyond the heliopause, a region where low-energy particles streamed outward along magnetic field lines and cosmic ray intensities reached only 90% of levels farther out. Another transition zone, another layer of complexity at the boundary. The crossing isn't instantaneous in every respect. Some properties change abruptly, others transition more gradually. The cosmic ray spectra Voyager measured provide detailed information about particle energies. Hydrogen and helium spectra show broad peaks from 10 to 40 million electron volts per nucleon. The distribution of energies reveals how cosmic rays are accelerated throughout the galaxy and how they propagate through space. These measurements help scientists understand not just the local environment, but galactic-scale processes. One puzzle remains from the termination shock crossing years earlier. Scientists predicted cosmic ray ions would reach maximum intensity at the shock, bouncing back and forth, gaining energy with each bounce, becoming high-speed particles. But Voyager 1 didn't find that maximum at the shock. Instead, cosmic ray intensity continued increasing as the spacecraft moved farther beyond the shock, through the heliosheath, toward the heliopause. The source of those cosmic rays is somewhere else, a region yet to be identified, a process still not fully understood. The termination shock itself surprised researchers in multiple ways. Scientists expected solar wind speed would drop to a few 100,000 miles per hour beyond the shock. Voyager found much lower speeds. Sometimes the wind appeared to flow backward, toward the sun. The first time instruments detected wind blowing back at the spacecraft. Completely unexpected behavior. The magnetic field's zebra stripe pattern, alternating field directions carried outward by solar wind, changed beyond the shock. As the sun rotates every 26 days, the field alternates every 13 days. Inside the termination shock, those stripes move rapidly past the spacecraft. Beyond the shock, the stripes slowed dramatically. It took more than 100 days for one stripe to pass Voyager. The pattern moved at nearly the spacecraft's speed, almost synchronized. That wasn't predicted either. These discoveries forced scientists to rethink models of the heliosphere. The boundary regions, termination shock, heliosheath, heliopause, behave differently than expected. They're more complex, more variable, more surprising than decades of theoretical work suggested. Direct measurements revealed reality doesn't match simplified models. And Voyager keeps going. Both spacecraft continue operating, continue transmitting, continue revealing properties of interstellar space. As of February 2026, Voyager 1 is 172.12 astronomical units from Earth. Voyager 2 is at 143.05 astronomical units. They're the most distant human-made objects ever created, still functional, still sending data across billions of kilometers of space. Their continued operation depends on failing power systems and aging components. But for now, they persist, measuring magnetic fields, detecting cosmic rays, monitoring plasma density, mapping the very local interstellar medium. Every transmission adds another piece to humanity's understanding of the space beyond the sun's influence. The space where our solar system ends and the galaxy truly begins. The hydrogen wall represents another unexpected structure at the heliosphere's edge. Voyager first detected it in 1992, a region where neutral hydrogen from interstellar space piles up as it encounters the heliosphere. Not charged particles affected by magnetic fields, but neutral atoms responding to different forces. The wall forms where interstellar hydrogen gets slowed and compressed by interaction with the heliosphere's boundary. Like water piling up against a dam, the density increases, the atoms accumulate, creating a detectable structure that New Horizons spacecraft confirmed again in 2018, 26 years after initial detection. Same feature, still there, still marking the transition zone where solar and interstellar material meet. Scientists predicted this wall would be hot hydrogen, temperatures elevated by compression and interaction. The observations confirmed the prediction, but the exact physics remains complex. How neutral atoms behave at this boundary differs from charged particle behavior. They respond to different forces, follow different paths, create different structures. The hydrogen wall provides crucial information about that neutral component of the interstellar medium, something Voyager's charged particle instruments couldn't fully measure. A complementary piece of the boundary puzzle. Meanwhile, scientists expected something else entirely that Voyager never found. A bow shock. Picture a boat moving through water. The bow creates a shock wave ahead of the boat, a visible V-shape spreading outward. For decades, scientists assumed our solar system's motion through the interstellar medium would create something similar, a bow shock forming ahead of the heliosphere where our bubble pushes through interstellar space. Theoretical models included it. Diagrams showed it. Everyone expected Voyager would detect it before reaching the heliopause. Voyager found nothing. No bow shock. The expected structure wasn't there. Data from NASA's Interstellar Boundary Explorer spacecraft confirmed the absence in 2012. Combined with Voyager observations, the conclusion became clear. The heliosphere has no bow shock, at least not in the traditional sense. This absence forced scientists to reconsider fundamental assumptions about the solar system's motion through the galaxy. If the local interstellar medium was supersonic, moving faster than sound speed in that medium, a bow shock would definitely form. The physics demands it, but recent data suggests the interstellar flow is subsonic instead, moving slower than expected. That changes everything. No supersonic flow means no bow shock. The heliosphere doesn't crash through the interstellar medium like a speedboat through water. It drifts more gently. The interaction is calmer. The boundary forms differently. Or perhaps the physics at this boundary differs from simple models entirely. Maybe factors scientists haven't fully considered affect how the interaction plays out. Either way, the missing bow shock represents another surprise. Another assumption overturned by direct observation. Reality keeps contradicting expectations. The heliosphere itself has an asymmetric shape that reveals interstellar magnetic field influence. It's not a perfect sphere expanding equally in all directions. Instead, the interstellar magnetic field drapes around the heliosphere, creating higher magnetic pressure on one side. That pressure pushes the boundary inward. The southern part of the heliosphere gets compressed more than other regions. The termination shock isn't centered on the Sun. It's offset about 32 astronomical units tailward, 27 units north, 12 units to the port side. The Interstellar Boundary Explorer confirmed these offsets independently. The closest region of the termination shock sits roughly 20 degrees south of the interstellar inflow direction. Minimum distance around 74 astronomical units. That asymmetry reveals how external forces shape the Sun's protective bubble. The heliosphere responds to pressure from outside, gets pushed and deformed, becomes lopsided rather than symmetric. This shape resembles a comet more than a sphere, roughly spherical on one side, extending about 100 astronomical units. But on the opposite side, a tail stretches for thousands of astronomical units. The heliotail, a vast stream of solar material trailing behind as our solar system moves through the galaxy. Voyager is heading toward the nose of this comet shape, the front, where the heliosphere pushes against oncoming interstellar material. The tail extends in the opposite direction, far beyond where any spacecraft will travel for centuries. The heliosphere also changes over time. It's not static. The Sun's 11-year activity cycle affects everything. During solar maximum, increased solar wind output makes the heliosphere larger. During solar minimum, reduced output lets it contract, like a lung expanding and contracting with breath. The boundary moves. The heliopause isn't fixed at one distance. Future spacecraft crossing it might find it at different locations, depending on where the Sun is in its cycle. This dynamic nature means Voyager's measurements capture the heliosphere at specific moments in its breathing cycle. Voyager 1 crossed during different solar conditions than Voyager 2. That partially explains why their crossings showed different characteristics. They sampled the boundary at different times, different solar wind conditions, different states of the heliosphere's expansion and contraction. Inside the heliosphere, plasma is hot and sparse. Solar wind creates this environment, millions of degrees Kelvin, but extremely low density. Outside, interstellar plasma is colder but denser. That fundamental difference marks the transition from solar-dominated to interstellar-dominated environment. Different temperature, different density, different composition. The properties flip at the boundary. Hot sparse plasma inside gets continuously replenished by solar wind streaming outward. The Sun constantly pumps new material into the heliosphere, maintains the pressure, keeps the bubble inflated. Without that continuous flow, the heliosphere would collapse. Interstellar pressure would overwhelm it. But the Sun's output continues. The wind flows. The bubble persists. The colder, denser interstellar plasma is part of the local interstellar cloud our solar system currently travels through. That cloud has its own properties, its own density and temperature, its own magnetic field structure. The heliosphere moves through this cloud like a submarine through ocean water. The cloud's properties determine how strongly it pushes back against the heliosphere, how much it compresses our protective bubble. Understanding these plasma properties helps scientists model stellar wind interactions everywhere, not just for our Sun. Every star with a wind creates its own heliosphere-like structure. different stars, different wind strengths, different surrounding environments. But the basic physics remains similar. What Voyager learns about our heliosphere applies to understanding how other stars interact with their galactic neighborhoods. One curious finding: the very local interstellar medium appears remarkably quiet. Voyager 1 measured very small magnetic fluctuation intensity beyond the heliopause. Scientists expected more turbulence, more variation, more chaos in the magnetic fields. Instead, the interstellar medium right outside our heliosphere shows surprising calmness. The fields are relatively steady. The fluctuations are minimal. Why so quiet? That remains unclear. Maybe we're in an unusually calm region of the local interstellar cloud. Maybe the heliosphere itself affects nearby interstellar space, creating a calmer zone immediately outside the boundary. Or maybe current instruments aren't sensitive enough to detect smaller scale turbulence that exists. But the measurements show less variation than expected. Another surprise to add to the list: in 2020, both spacecraft recorded something new. Voyager 1's magnetometer registered an abrupt jump in magnetic field intensity. Its plasma detector measured rising plasma density. At first, researchers attributed these changes to solar effects, surges of solar plasma smashing against the heliosphere boundary, creating swells that reverberate through interstellar space, compression waves from the sun reaching beyond the heliopause, temporary disturbances from our star's activity. But the anomalies didn't abate. They continued, persisted far longer than expected. That raised questions. If these changes came from the sun, they should be temporary, transient effects that pass as the solar disturbance moves by. Instead, the elevated fields and density remained. Months passed. The readings stayed high. Some mission scientists began questioning whether the sun caused these changes at all. Maybe Voyager encountered something else entirely, a new type of interstellar structure, a region of naturally higher density in the local interstellar medium, or perhaps some other phenomenon scientists haven't yet identified. The mystery remains unsolved. Data continues arriving. Scientists keep analyzing, but no definitive explanation has emerged. This demonstrates that even after crossing into interstellar space, Voyager keeps encountering unexpected phenomena. The journey doesn't end at the heliopause. New discoveries wait farther out. The interstellar medium has its own complexity, its own structures, its own mysteries to reveal. October 2020 brought another significant finding. Both spacecraft detected a substantial, unexpected increase in density beyond the solar system. The measurements suggested this density gradient is a large-scale feature of the very local interstellar medium in the direction of the heliospheric nose. Not a temporary anomaly, not a local fluctuation, but a genuine trend. Increasing density as Voyager travels farther into interstellar space. This increasing density has implications. It suggests the local interstellar medium isn't uniform. Density varies. Maybe the medium is being compressed ahead of the heliosphere. Maybe our solar system approaches a denser region of the interstellar cloud. Or maybe the structure of the cloud itself naturally has density variations that Voyager is now sampling. Whatever the cause, the discovery challenges assumptions about a uniform interstellar medium. Space between stars has structure, has variation, changes from place to place. These measurements help scientists understand the local interstellar cloud through which our solar system moves. That cloud has boundaries, has internal structure, has regions of different density and temperature. Voyager is mapping it, one measurement at a time. Each data point adds detail to our understanding of the neighborhood through which the sun travels. The spacecraft also detected what scientists call interstellar flux tubes, structures where particles from outside somehow intrude into the heliosphere before the heliopause. Voyager detected interstellar particles on 2 separate occasions, while still technically inside the boundary. How did those particles get there? The flux tubes, temporary channels or filaments that allow interstellar material to penetrate the heliopause, like leaks in the hull of a ship. One of Voyager's instruments showed particles from inside the heliosphere slipping through the boundary into interstellar space. The boundary leaks both ways, not perfectly sealed, not a solid wall, more porous than simple models suggested, and the permeability varies by location. Voyager 1 exited near the front of the heliosphere, the nose pushing into oncoming interstellar flow. That region appears more tightly sealed. Voyager 2 crossed closer to the flank. That region seems more porous, easier for particles to cross, more leakage in both directions. This asymmetric permeability reveals the boundary's complexity. It's not uniform. Properties change depending on location. Some regions are tighter, others more porous. The structure depends on local magnetic field geometry, on the angle between solar and interstellar fields, on pressure variations around the boundary. All these factors create a complicated, three-dimensional structure that varies from place to place. The discovery challenges the notion of the heliopause as an impermeable boundary. It's more like a fuzzy transition zone with varying properties. Particles can cross under certain conditions, in certain locations. The boundary exists, but it's not absolute, not perfectly defined. More nuanced than early models suggested. Both Voyager crossings showed increased plasma density before and after the boundary. Compression on both sides, higher than expected density. This suggests interstellar pressure shapes the heliosphere's outer layers more actively than models predicted. The interstellar medium pushes back harder, compresses the boundary region, creates density enhancements both inside and outside the heliopause. That compression affects how the boundary behaves, affects its permeability, affects particle acceleration near the boundary, affects magnetic field behavior. The pressure from outside influences everything about how the heliosphere's edge forms and evolves. Scientists are incorporating these observations into updated models, trying to capture the complexity Voyager revealed. Every discovery raises new questions. Every answer reveals deeper mysteries. The spacecraft keep traveling, keep measuring, keep sending data back across billions of kilometers. And scientists keep learning, keep revising theories, keep uncovering how our solar system fits into its galactic environment. The edge of the solar system isn't simple, isn't clean, isn't predictable. It's a dynamic, complex, surprising place where solar influence fades and galactic environment begins, where two different plasma environments meet and interact, where boundaries leak and compress and shift over time. where spacecraft designed in the 1970s continue revealing secrets no one anticipated when the mission launched. Yet there's something stranger happening further out, something that puzzles mission scientists even now. In 2020, Voyager 1's magnetometer registered an abrupt jump in magnetic field intensity, not during a solar outburst, not during any obvious event. The intensity just increased and stayed elevated. Plasma density rose simultaneously, two separate instruments showing correlated changes. Scientists initially thought solar eruptions caused it. The sun periodically ejects massive plasma clouds. Those clouds slam into the heliopause, create pressure waves that propagate outward into interstellar space, compress the interstellar plasma, intensify its magnetic field. That explanation worked for the first few events. But the anomalies that began in 2020 didn't abate. They persisted, month after month, year after year. Mission scientists started questioning the solar origin hypothesis. If these changes came from the sun, they should be transient, temporary, fading as the pressure wave passes. But Voyager keeps measuring elevated field strength, higher density, something sustained. Does Voyager 1 travel through a new type of interstellar structure? A region where the local interstellar medium naturally has higher density or stronger magnetic fields? Or does the sun's influence extend further than models predict, creating long-lasting effects beyond the heliopause? No definitive answer yet, just ongoing measurements, continued mystery. Another example of how interstellar space refuses to match predictions. Meanwhile, the spacecraft themselves approach their inevitable silence, not from dramatic failure, from simple power depletion. Voyager 1 and 2 carry plutonium-238 radioisotope thermoelectric generators. The plutonium decays, generates heat. Thermocouples convert that heat to electricity. Elegant system, no moving parts, no sunlight required. Perfect for deep space missions lasting decades, but plutonium decays constantly. Heat output drops. Available power decreases year by year. Engineers have managed the decline carefully, turning off heaters, shutting down non-essential systems, prioritizing the science instruments that provide unique data from interstellar space. As of early 2026, Voyager 1 sits at 172 astronomical units from Earth, Voyager 2 at 143 astronomical units, both still functioning, still transmitting, still measuring the interstellar environment. Each generates approximately 220 watts, down from 470 watts at launch. Not much power. A couple of old-fashioned incandescent bulbs. That dwindling supply determines mission longevity, not instrument failure, not communication loss, just insufficient power to run the instruments and transmit data back. Mission managers estimate the spacecraft can operate into the early 2030s, maybe a few years longer with careful power management. Then the final instruments will shut down. Signals will cease. The spacecraft will continue coasting outward, silent, dark, carrying their golden records, messages from Earth encased in gold-plated copper, images, sounds, music, greetings in 55 languages. Those records will outlast Earth itself, probably outlast the Sun. Voyager 1 and 2 will orbit the galactic center for billions of years, occasionally passing through interstellar clouds, sometimes encountering other stars heliopause regions, always moving, never returning. But before silence falls, the data keeps flowing. Every measurement adds detail. Every observation refines models. Every anomaly reveals how much remains unknown. Consider what Voyager has accomplished. 2 spacecraft launched in 1977, built with 1970s technology, before personal computers, before the internet, before cell phones, before digital cameras. Those spacecraft explored Jupiter, discovered active volcanoes on Io, revealed the intricate structure of Saturn's rings, found new moons, measured planetary magnetic fields, revolutionized understanding of the outer solar system, then kept going into regions never before explored, past Neptune, past Pluto, into the helios sheath, through the heliopause, into interstellar space itself. They've traveled longer than any human mission, operated longer than any spacecraft, returned data from further away than any probe before them. And they've revealed that the edge of the solar system isn't what anyone expected. Not clean, not simple, not predictable. A complex, dynamic, surprising boundary where solar dominance fades and galactic environment takes over. The heliosphere itself appears more complicated than models suggested. Not spherical, not static, asymmetric, variable, responding to solar activity, shaped by interstellar pressure. Compressed in some directions, extended in others. The heliopause leaks. Particles cross in both directions. Magnetic fields align unexpectedly. Temperature varies wildly. Density changes unpredictably. Everything about the boundary challenges simple descriptions. Scientists once thought they understood heliospheres. The Sun creates one. Other stars probably create similar structures. Simple concept, straightforward physics. Voyager showed otherwise. The details matter. The complexity matters. Every heliosphere likely differs based on its star's output and the interstellar environment it encounters. That knowledge extends beyond our solar system, helps astronomers understand exoplanet environments, stellar winds around other stars, how cosmic rays affect planetary atmospheres, the habitability of worlds orbiting different types of stars. The heliosphere shields Earth from most galactic cosmic rays. Voyager 1 measured that protection, over 70% reduction. Without that shield, Earth's atmosphere would receive far more radiation. Life's evolution might have taken different paths, or struggled to develop at all. Other stars have different winds, different magnetic fields, create different heliospheres. Some might offer less protection, others more. The details shape whether planets can maintain atmospheres, whether life can thrive. Voyager's measurements provide the ground truth, the actual data against which models are tested. Future missions to other stars will need to account for these complexities, and the spacecraft still have more to teach. As they continue outward, they'll measure how the very local interstellar medium varies, map density gradients, track magnetic field changes, detect structures in the local interstellar cloud. That cloud, the local interstellar cloud, extends for several light years. Our solar system entered it thousands of years ago, will remain inside for thousands more. Voyager samples its properties, measures its structure, provides data no other mission can. Eventually, the spacecraft will pass through the cloud's far boundary, enter different interstellar regions, but their power will likely fail before reaching that transition. the data stream will end while still inside the local cloud. What comes after silence? Just trajectory. Voyager 1 heads toward the constellation Ophiuchus, will pass within 1.6 light-years of the star Gliese 445 in about 40,000 years. Not close enough to be captured, just passing through that star's neighborhood. Voyager 2 heads towards Sirius, will come within 4.3 light-years in about 296,000 years. Again, not close enough for gravitational capture. Just another waypoint in eternal wandering. Both spacecraft will orbit the galaxy, rising and falling through the galactic disk, passing through spiral arms, occasionally encountering molecular clouds, always moving at about 17 kilometers per second relative to the Sun. That velocity insufficient for escaping the galaxy, too fast for stellar capture. They'll witness events no human will see. Stellar evolution, supernova explosions from relatively close range, the slow transformation of galactic structure, the eventual collision between Milky Way and Andromeda galaxies in 4 billion years. Silent witnesses to cosmic history, carrying humanity's message, a gesture of communication from a species that briefly emerged on one world, looked outward, built machines to explore, and sent them into the infinite. The golden records preserve that moment. 1977, when humans could launch such missions, when the planets aligned favorably, when technology and ambition converged, when 2 spacecraft began journeys that continue 5 decades later. Those records contain images of Earth, mathematical definitions, the structure of DNA, photographs showing human diversity, sounds of nature, music spanning cultures and centuries, greetings speaking humanity's linguistic diversity. Any civilization finding these spacecraft millions or billions of years hence will discover artifacts from a vanished world. They'll decode the instructions, play the records, encounter humanity through carefully curated messages. Will they understand? Possibly. The records include mathematical and scientific information, universal constants, physical principles any technological civilization should recognize. Will they care? Unknown. Perhaps they'll find these ancient probes archaeologically interesting, perhaps merely puzzling. Perhaps they'll never be found at all, drifting eternally through interstellar space, passing between stars without notice. But the gesture matters. The attempt to communicate across cosmic distances and timescales represents something fundamental about human nature. The drive to explore, to reach beyond known boundaries, to leave traces proving we existed. Voyager embodies that drive. 2 spacecraft carrying our message, our science, our curiosity, our hope that someone, somewhere, sometime might find them and know humanity briefly flourished. And until that distant possibility, the mission continues. Data flows. Scientists analyze. Knowledge grows. The edge of the solar system reveals itself measurement by measurement. The boundary between solar and galactic environments becomes clearer. The complexity deepens. Every discovery raises questions. Every answer reveals deeper mysteries. The universe refuses to be simple, refuses to match predictions, continues surprising us. That's the real legacy, not the distance traveled, not the longevity. The revelation that even familiar territory, the space around our own sun, contains profound mysteries, that boundaries are complex, that nature resists simple categorization. The solar system has no clean edge, No definite ending, just gradual transition from solar dominance to galactic environment, multiple boundaries, overlapping regions, asymmetric structure, temporal variation, spatial complexity. Voyager showed us that truth, continues showing us. Will keep revealing details until power finally fails and silence falls. And even then, the spacecraft keep going, moving outward, carrying their messages, traversing the galaxy for epochs beyond human comprehension, physical embodiments of humanity's brief moment of consciousness and curiosity, our emissaries to eternity, our footprints in the cosmic sand. The spacecraft keep transmitting, keep measuring, keep sending data back across distances that take over 23 hours for light to cross. That delay matters. When scientists send a command to Voyager 1, it takes 23 hours to arrive. The spacecraft executes the command, sends confirmation back. Another 23 hours, nearly 2 full days for a single exchange. A conversation stretched across billions of kilometers at the speed of light itself. Yet that conversation continues. Engineers monitor power levels, adjust instrument operations, prioritize data collection, maximize what little time remains, because the end approaches. Not suddenly, not catastrophically, just the steady, inevitable decline of plutonium-238 decaying in the radioisotope generators, heat output dropping, available electricity decreasing. By the early 2030s, maybe a few years beyond with careful management, insufficient power will remain. The last instrument will shut down. The final transmission will cease. Then silence, not failure, not loss, just completion. The mission will have extracted every possible measurement from humanity's first journey into interstellar space. Consider what those measurements revealed. A boundary far more complex than anticipated. A heliopause that leaks, that shifts, that varies by location and time. Temperature extremes creating a wall of fire where charged particles compress and heat to tens of thousands of degrees, while adjacent regions stay cool. Magnetic fields that align impossibly. Cosmic rays that intensify beyond where models predicted. Plasma densities that jump 80-fold at the boundary. Solar wind that sometimes flows backward. A stagnation region nobody expected. Interstellar structures detected through persistent density changes and magnetic field anomalies. Every discovery challenged assumptions. Every measurement revealed complexity. The edge of the solar system refused to match the clean, simple picture scientists had constructed. That's the deeper lesson. Reality exceeds models. Nature resists simplification. The universe contains layers of complexity that reveal themselves only through direct observation. No amount of theoretical work could have predicted what Voyager found. The calculations were elegant, the simulations sophisticated, the predictions logical, and substantially wrong about crucial details. Only by going there, actually traveling to the boundary and measuring it directly, could scientists discover what truly exists at the solar system's edge. This principle extends beyond heliospheres. It applies everywhere, to planetary atmospheres, to stellar evolution, to galactic dynamics, to cosmic structure formation. Theory guides, observation corrects, direct measurement reveals truth that mathematics alone cannot capture. Voyager 1 and 2 demonstrated that principle at the grandest scale yet attempted. They ventured into the unknown and found it stranger than imagined. the spacecraft also revealed something about human capability. In 1977, engineers built two probes using technology that seems primitive by modern standards. Computers with less processing power than a contemporary calculator, instruments that could fit in a suitcase, power systems generating barely more electricity than a couple of light bulbs. Those machines operated flawlessly for 5 decades, survived radiation, extreme cold, micrometeorite impacts, the accumulated damage of 50 years in space. They kept functioning, kept transmitting, kept delivering science. Modern spacecraft often fail within years, sometimes months. The Voyagers persist, not through luck, through brilliant design, through engineering that prioritized reliability over capability, through systems built to last when lasting meant everything. The golden records they carry represent a different kind of achievement, not technological, cultural, philosophical. The decision to include messages for potential alien civilizations showed humanity at its most optimistic, most hopeful, most willing to believe in possibilities beyond immediate evidence. Those records preserve a moment. 1977, when humans looked outward with wonder rather than fear, when space exploration seemed limited only by imagination, when the future felt infinite. The messages encoded on gold-plated copper include mathematical principles, images of Earth, sounds of nature, music spanning cultures, greetings in 55 languages. Carl Sagan and his team carefully curated content representing humanity's diversity and achievement. Any civilization finding these artifacts millions of years hence will encounter humanity frozen in that moment of optimism. They won't know what came after, won't know whether humans survived, whether we spread through the cosmos or destroyed ourselves, whether we ever developed interstellar travel or remained confined to one star system. They'll only know we existed. We built these machines. We sent them into the void carrying messages. We hoped someone might find them and understand. That hope matters more than the probability of discovery. The gesture itself, the act of reaching across cosmic distances and timescales, defines something essential about human consciousness. We seek connection. We want to be known. We refuse to accept isolation, even when separated by light years and eons. Voyager embodies that refusal. 2 spacecraft carrying humanity's message into eternal wandering. Not because the message will likely be received, because sending it affirms our existence, our curiosity, our hope. Meanwhile, the science continues. Every remaining day of operation adds value. The spacecraft measure how the very local interstellar medium varies, how density changes with distance from the heliopause, how magnetic fields evolve in interstellar space, how the local interstellar cloud structure affects its properties. These measurements can't be obtained any other way. No telescope can resolve such fine detail at interstellar distances. No model can predict variations without ground truth for calibration. Only by traveling through the region and measuring it directly can scientists map its properties. Voyager provides that irreplaceable data. The spacecraft sample the interstellar environment, record its characteristics, transmit findings back across billions of kilometers. Each data point adds detail to humanity's understanding of the space between stars. That space isn't empty, isn't uniform, isn't boring. It contains structure, variation, complexity matching anything found within solar systems. The interstellar medium has its own dynamics, its own weather, its own mysteries. Scientists once viewed it as mere background, empty space between interesting objects. Voyager revealed otherwise. Interstellar space has properties worth studying, structures worth mapping, physics worth understanding. The very local interstellar medium through which Voyager travels right now, the region immediately beyond the heliopause, differs from the wider interstellar medium. It's been shaped by interaction with the heliosphere, compressed by pressure from the solar wind, modified by magnetic fields from the sun. This boundary region extends for multiple astronomical units beyond the heliopause. Voyager is mapping it, measuring how properties transition from nearly solar to fully interstellar. How the sun's influence fades with distance, where galactic environment finally dominates completely. Future missions might follow Voyager's path. New spacecraft with more advanced instruments, better power systems, upgraded communications. They'll build on Voyager's discoveries, explore regions Voyager couldn't reach, answer questions Voyager raised, but they'll do so decades from now, maybe longer. Currently, no funded mission targets interstellar space. No spacecraft capable of reaching the heliopause within human lifetimes exists beyond Voyager itself. The New Horizons probe, which explored Pluto, continues outward. It might eventually reach the heliopause, but not for decades. And it carries fewer functioning instruments than Voyager, less power, shorter operational life expectancy. So Voyager remains humanity's primary source of direct interstellar measurements, the only functioning spacecraft beyond the solar system's edge, the sole providers of ground truth about what exists out there. When the spacecraft finally falls silent, that data stream ends. Scientists will retain everything transmitted, will analyze it for years, extract every possible insight, but no new measurements will arrive. The exploration of interstellar space will pause until someone launches the next mission, until technology and funding align, until humanity again commits resources to exploring beyond the solar system's boundary. That commitment seems uncertain. Space exploration budgets remain modest. Priorities shift. Decades separate major missions. Interstellar probes require patience, commitment, willingness to support projects that won't return results within single careers or lifetimes. Voyager demonstrated what such commitment achieves, what patience enables, what results from building machines designed to last and supporting them across decades. The spacecraft launched before personal computers existed, before the internet, before cell phones, before digital photography, using technology that seems ancient now, yet they still function, still explore, still return science impossible to obtain any other way. That achievement stands regardless of what follows. Voyager 1 and 2 accomplished their mission, explored the outer planets, reached interstellar space, measured the boundary, revealed its complexity, transmitted data that transformed understanding. Everything beyond this point is bonus. Extended mission, unexpected longevity, additional science from regions no mission planner in 1977 imagined the spacecraft would reach. The plutonium keeps decaying, the power keeps dropping, the end keeps approaching. But until that moment arrives, Voyager continues its primary function: measuring, recording, transmitting, teaching humanity about the cosmos we inhabit. The wall of fire at the solar system's edge turned out to be real, not metaphorical. Actual superheated plasma reaching tens of thousands of degrees. Trapped particles compressed at the boundary, creating temperature extremes that defy simple explanation. Spacecraft survive it only because the density is too low to transfer heat effectively. The fire exists but cannot burn, cannot damage, can only be measured and marveled at. That paradox captures something about the boundary itself. It exists, definitively, measurably, yet it's more complex than simple existence suggests, more nuanced than any single description captures. The heliopause is a boundary, but also a transition zone, a region of mixing and interaction, a dynamic interface responding to pressure from both sides. It shifts position, changes character, varies by location, leaks particles in both directions. Defining where the solar system ends becomes surprisingly difficult when examined closely. The heliopause marks one boundary, but solar wind continues beyond it, briefly. Cosmic rays penetrate inward from it. Magnetic fields connect across it. The transition isn't instantaneous or complete. Perhaps that's the fundamental insight. Nature doesn't do clean boundaries, doesn't create sharp divisions, produces gradients instead, transition zones, regions where properties shift gradually or chaotically, but rarely instantaneously. The solar system doesn't end at a specific distance. It fades, its influence diminishes, galactic environment gradually dominates. Multiple boundaries exist: termination shock, heliopause, hydrogen wall, each marking different aspects of the transition. Voyager mapped those boundaries, measured them, revealed their complexity, showed that even the space around our own star contains profound mysteries. And the spacecraft keep going, outward, always outward, measuring what they can, transmitting what they measure, until power fails and silence falls. Then they'll continue without us, without communication, without awareness of their own journey, just inert machines coasting through the galaxy, carrying messages from a world they'll never revisit, traveling distances they'll never comprehend. In 40,000 years, Voyager 1 passes near Gliese 445. In 296,000 years, Voyager 2 approaches Sirius. Distant future encounters with other stars, other solar systems, other potential heliopause boundaries. But those crossings will happen in silence. No instruments to measure them, no transmitters to report findings. Just two ancient spacecraft drifting past, carrying gold records from a civilization long gone. Unless humanity survives that long. Unless we spread through the galaxy ourselves. Unless our descendants encounter Voyager, wandering the cosmic depths, and retrieve it. Bring it home. Place it in a museum celebrating the first human-made objects to leave the solar system. That future seems distant, speculative, uncertain. But so did interstellar travel in 1977, when Voyager launched. The spacecraft proved it possible. Not practical, perhaps. Not easy, certainly. But possible. Two machines, built with 1970s technology, reached interstellar space and survived there. Operated there. Returned science from there. If machines built 50 years ago can achieve that, what might machines built 50 years hence accomplish? What might humans themselves accomplish given sufficient time and determination. Voyager suggests the answer. We can reach beyond our solar system, can explore interstellar space directly, can measure what exists out there and transmit that knowledge home. The question isn't whether we can, it's whether we will, whether we'll commit resources to such endeavors, whether we'll maintain patience across decades required for results, whether we'll value knowledge for its own sake enough to pursue it into the cosmic dark. Voyager demonstrates we once did, once prioritized exploration, once built machines to last, once sent them into the unknown because the unknown beckoned. The spacecraft continue that journey now, measuring, recording, transmitting, teaching, revealing, until the day they can't, until power fails and silence claims them. But the data survives, the knowledge endures, the discoveries remain. Humanity learned what exists at the solar system's edge because 2 spacecraft traveled there and measured it directly. That achievement stands permanent. Whatever follows, whether new missions or decades of silence, Voyager proved it possible, showed the way, revealed what awaits beyond the boundary. The wall of fire is real. The boundary is complex. Interstellar space beckons, and we've touched it, briefly, tentatively, but genuinely. 2 spacecraft from Earth crossed into the space between stars and survived to report what they found. That's the story. That's the achievement. That's what Voyager revealed at the edge of our solar system, where solar influence fades and the galaxy begins.